Now, when we start to replace atoms here with lone pairs, the lone pair is going to occupy a spot that will minimize the small bond angles. So in this case, 90-degree bond angles. So if we have the 5 areas of electron density, one of them being a lone pair and then 4 attached atoms, we'll get the smallest number of 90-degree bond angles with that lone pair if it's on an equatorial position. That means it has a 90-degree bond angle with 2 of the axial positions. If we try to put the lone pair on the axial position, then we would end up with 3 90-degree bond angles with each of the equatorial positions. So the lone pair goes where it will minimize the small degree bond angles. So with the lone pair on our equatorial position, we end up with a structure that looks like this. We rotated it from the previous structure having the axial in the vertical position because this shows where the name comes from. So if we set these 2 atoms on the ground, the 2 axial atoms can just bounce up and down, and it becomes like the schoolyard equipment called the seesaw or teeter-totter seesaw. So we call this the seesaw molecular geometry. This comes from our trigonal bipyramidal electron geometry. The bond angles here are going to be the same set for the trigonal bipyramidal. We have a 90-degree bond angle between the axial and equatorial position, 120 between the 2 equatorial positions, and 180 between the 2 axial positions. If we have our 5 areas of electron density, 2 of them being lone pairs, 3 of them being atoms. We're starting off with our trigonal bipyramidal electron geometry. Our lone pairs are again in the equatorial position. This minimizes the 90-degree bond angles between the lone pairs and other atoms. So with our 2 lone pairs in the equatorial position, we're left with this structure, the 2 axial atoms and 1 side atom sticking off perpendicular. So we end up with a T-shaped molecule, T-shaped molecular geometry. So the bond angle is going to be 90 degrees between the axial and the equatorial, and 180 degrees between the 2 axial bond angles. And it will actually be slightly less than that because of the repulsion of the lone pairs. If we have those 5 areas of electron density, 3 of them being lone pairs and 2 of them being atoms. So again, the lone pairs are taking up the equatorial positions and we're left with the axial positions being occupied by the atoms. So we're going to end up with a linear molecular geometry on this one with only 1 bond angle of 180 degrees between the 2 axial positions. So this linear molecular geometry comes from the trigonal bipyramidal electron geometry. And the bond angle will be 180 degrees. It's not going to be less than that because these 3 lone pairs are forming a balanced collar around the central of the atom. Going up in areas of electron density, up to 6 areas of electron density, we're going to end up with the octahedral structure. So we have 6 atoms, we're calling it octahedral. Well, if we put in surfaces on all the sides of this, we're going to have a 4-sided pyramid on top and a 4-sided pyramid on bottom. So we have 8 sides. They're all identical sides, so we have an octagon. We're going to call it octahedral geometry. So we have our 6 atoms attached, and again, we have to be period 3 or higher to have access to the d orbitals, so we can exceed the octets. So with 6 atoms attached, we have this octahedral geometry. So the bond angle is going to be 90 degrees between any 2 adjacent atoms. So we're going to have a square, a flat square in the middle here with an atom on top and bottom, creating a top pyramid and a bottom pyramid, and just 90-degree bond angles between all the atoms present. If we have this 6 areas electron density, one of them being a lone pair, all atoms, all positions are identical, so it doesn't matter which one we're replacing here with the lone pair. We replace it with a lone pair. We just orientate it so that lone pair is on the bottom here, and what we're left with is a square base with a peak in the center, so it becomes a square pyramid. So that we have our square pyramid molecular geometry. If we have our 6 areas electron density, 4 of which are atoms and 2 are lone pairs. So the first lone pair could be anywhere, but the second lone pair has to be opposite the first lone pair. Because if it was not opposite, then it would have a 90-degree bond angle between the 2 lone pairs, and that's too repulsive. So the 2 lone pairs have to be opposite each other. That leaves the 4 remaining atoms in a square plane in the middle. So this is our square planar molecular geometry. This comes from our octahedral electron geometry. So the bond angle is going to be 90 degrees between adjacent atoms, 180 degrees between opposite atoms. So we have bond degrees of 90 degrees and 180 degrees. When we only have 2 atoms, it doesn't matter how many lone pairs we have on what we consider to be the central atom. Doesn't matter how many lone pairs we have on there. Doesn't matter if we have single, double, or triple bonds. When we have only 2 atoms present, they are always linear. There is no possibility to be anything else. As they say in math, 2 points define a line, so 2 atoms are linear. And we need 3 atoms to have a bond angle, so there is no bond angle associated with any diatomic molecules. So just to summarize some of the geometries based on number electron domains on the central atom. If we have 2 areas electron domains, we're going to have a linear molecular structure. So we're saying 2 binding domains. That means 2 atoms and no lone pairs. Non-binding domains is no lone pairs. So we have 2 atoms attached, no lone pairs. We're going to have a linear structure. And it doesn't matter whether we have 2 double bonds as in carbon dioxide, a single and triple as in hydrogen cyanide, or 2 single as in beryllium hydride. If we have 3 electron domains, if they're all bonding domains, we have a trigonal planar molecule, bond angle of 120 degrees. If we have 2 bonding domains and 1 lone pair, it's going to be a bent molecule with bond angle being less than 120 degrees. With 4 electron domains, if all 4 are bonding domains, we're going to have a tetrahedral geometry with a bond angle of 109.5. 3 bonded atoms and 1 lone pair will give us a pyramidal structure, trigonal pyramidal structure. Sorry, this should be trigonal pyramidal structure. Bond angle will be less than 109.5. For ammonia, it's 107 degrees. For 2 attached atoms and 2 lone pairs, we're going to have a bent molecular structure. Bond angle is less than 109.5. For water, it's 104.5 degrees. For 5 areas electron domains, with 5 atoms attached, there's going to be a trigonal bipyramidal geometry. Bond angle is going to be a 90, 120, and 180. With 4 atoms and 1 lone pair, it's going to be a seesaw structure. Bond angles 90, 120, 180 degrees. 3 atoms and 2 lone pairs will give us a T-shaped structure, bond angles of 90 and 180 degrees. 2 atoms and 3 lone pairs will give us a linear structure, bond angle of 180 degrees. For 6 electron domains, if they're all atoms, no lone pairs, we have an octahedral structure. With 5 atoms and 1 lone pair, we're going to have a square pyramid. And with 4 atoms and 2 lone pairs, we're going to have a square planar structure. Let's summarize it based on the number of atoms attached to the central atom. So if we have one atom attached to the central atom, that means we only have two atoms overall. Two atoms is going to be linear, and there's going to be no bond angle. If we have two attached atoms to the central atom, the geometry now depends upon how many lone pairs we have. We only have two choices with two attached atoms. We have three atoms overall. They're either going to be linear or bent are the two choices. They're going to be linear when we have no lone pairs on it, or three lone pairs. That's the trigonal bipyramidal electron geometry with three lone pairs surrounding the equatorial positions, giving us the two axial atoms attached, creating a linear. If we have one lone pair or two lone pairs, we're going to have a bent structure. Bond angles will depend. Less than 120 degrees for one lone pair and less than 190 degrees for two lone pairs. And this is identifying the electron geometries. These are coming from on the right column. If we have three attached atoms, if we have no lone pairs, we're going to have a trigonal planar structure, bond angle 120 degrees. If we have one lone pair, we have a trigonal pyramidal structure. Bond angle will be less than 109 degrees. And if we have two lone pairs attached, we're going to end up with a T-shaped molecular geometry. For attached atoms, with no lone pairs, we'll have the tetrahedral geometry, 109.5 degrees bond angle. One lone pair will give us a seesaw structure, and two lone pairs will give us our square planar structure. 5 attached atoms with no lone pairs will give us trigonal bipyramidal, and one lone pair will give us a square pyramid. 6 attached atoms will be octahedral. If we have more than one central atom, so we don't have a single central atom, these will have larger complex geometries. Some of these geometries will be described in other fields such as organic chemistry. For this class, we're just going to describe geometry around each of the central atoms. So for the valence shell electron pair repulsion model, we're going to start off by drawing the Lewis structures for the molecules, any resonance structures. We can use any of the resonance structures to determine geometry. We're going to sum the electron domains, lone pairs and the bonds around the central atom to determine the electron geometry. Using electron geometry and the number of attached atoms and lone pairs, we can get the molecular geometry. This model successfully describes geometry of the molecules. It doesn't describe how geometries arise from the molecules, and we're going to use hybridization to show how we get the geometries from atomic orbitals. Once we know the geometry of the molecule, we can determine if the molecule is going to be polar or nonpolar. First step is determine the difference in electronegativity between atoms. If we have 0.4 or less for all these differences, we have a nonpolar molecules regardless. If our difference is greater than 0.4 for any one of the bonds, then we have the potential of having a polar molecule. We can still have a nonpolar molecule if the molecule is highly symmetric. The simple way of showing this is if all the attached atoms to the central atom are identical, and for octet-obeying structures, there are no non-binding pairs on the central atom. Now we're going to have, in addition to this rule, we're going to have two additional structures that allow us to have a nonpolar structure, highly symmetric molecule, when all the attached atoms are identical. So our symmetric geometries include linear geometry. So this will come with the 2 electron domains. It will also come with the linear molecular geometry coming from the trigonal bipyramidal electron geometry. Trigonal planar structure, tetrahedral structure, trigonal bipyramidal structure, octahedral structure, and one more, the square planar structure. These can all be nonpolar if all the attached atoms to the central atom are identical.